we are continue to study the main definition of the turbomachinery. So, and today we will make a lot of definition. I will try to draw a lot of sketch, but it's important for us because I will give to you a lot of definitions. We need to understand it to speak at one language. So it's the first, and after that I think we discuss the classification of the turbomachinery. We are trying to find what the main difference between the different type of the turbomachinery, and we will try to find what the type of the turbomachinery are best for different application. Maybe if we will have enough time, we will refresh the information about the working process of gas turbine engine, because we will discuss at the next step the different area of application of the turbomachinery. So let's start. I will share my screen. So, do you see the screen? Hello? Do you see it?
No.
No? Strange. Okay.
Yes, right now it's okay.
It's okay.
Yeah.
Sorry, 1 second. And now, okay?
Yes.
Perfect. So, as far as I remember, last time we stopped at the discussion of the geometrical parameters of the turbomachinery, and finally we discuss the parameters of the meridional cross section. So I refresh to you what these definitions, which we will discuss today, will be common for the different type of the turbomachinery. It's the common for the compressors and for the turbine, and it's mostly not depend from the type of the turbomachinery. It's common for the radial turbomachinery, for axial turbomachinery. Of course, some machines have special features, but in common the same principle. That's why I will try to explain the definition at the base of the axial compressors and the turbine. Here you see the pictures deal with the turbines, but maybe it will be a good idea to me to try to draw the compressor as example, but the definition will be the same. But very often when I want to draw the turbomachinery, I became to draw the turbine. That's why I will try to draw the compressor, but I could to receive the turbine. So the first part, the parameters of the meridional cross section, we are already discussed. Okay, let's discuss the parameters of the airfoils and the blade rows. So I will change the slide, so I free the space for the additional sketch. Okay, let's discuss step by step most important definition of the geometrical parameters of airfoil blade row. So 1 second. Okay, let's start. I will draw the blade. Looks strange. I will draw the sketch of the blade row. I will draw for the compressor. Unfortunately, I need to some skills to draw it. Ow. So looks strange, of course. This is the blade row. It must be compressor. Okay, let's start to discuss the definition. If you are not understand, I make the cross section of the blade row by cylindrical cross section, and after that I turn it at the plane. So, first definition, blade chamber line, this one for the turbine. What is the chamber line? We draw a lot of circles inside the profile, and after that connect all the sorry, 1 second. We connect all the centers of such lines. So if we are put inside the profile a lot of circles, which are have only one point at the pressure side and the suction side of the blade, and you need all the centers of such circles, we receive the blade chamber line. So, and I refresh for you what this part of the blade are called pressure side, this one, and opposite side are called suction side, the opposite. We will use such short names because we will very often will speak about the processes in the pressure side and the suction side. So it's the first definition, chamber line. So after that we are draw lines which are connect leading edge of all blades. This is leading edge. And we will draw the line which connect the trailing edge of all blades. So we are finally, for axial blade row, we are receive the straight line. And this line are called the front, blade row front. You see what we have two fronts, the inlet front and the outlet front. At this case, this is outlet front and this is inlet front. If we speak about the centrifugal compressor, centripetal turbine, the front will have the circle shape. It will be circle, it will be round. This definition will be important for us for set some other definitions. So what else? So you see what we have 2 points, points number 1 and point number 2, at which chamber line are how to say it, meet this the airfoil. So it's the points at which chamber line are cross the profile. The distance between these two lines are called chord. This one, chord. So important moment for you, especially for you, because you are foreigner, relative me. I will use Russian designation, the designation which are typically for the Russian turbomachinery school. But unfortunately, the designation which are used in England turbomachinery school, USA turbomachinery school, German turbomachinery school, a little bit different. And of course, it's very inconvenient because I think you will draw French books, you will, read, of course. You will read French books, you will read English turbomachinery books, and you will find the different designation. That's why it's a little bit inconvenient, but unfortunately I am based to the Russian sources. It's the first moment, but it's very easy to find the connection between the Russian designation and the foreign designation. The difference deal with the Russian and foreign turbomachinery schools a lot of time are developed separately and have no big connection. That's why we are speak about the same things, but we are using the different designation, and it's one problem. The second problem will be deal with the angles, and I will pay attention at it a little bit later, but especially for you, like for foreigners related to the Russian turbomachinery school, it will be very important because it's have the great influence to the formulas which you use, and you have the higher probability to meet other approach to measure angles, for example. So, and let's return back to the Hort. The distance between point 2 and point 1, this is 1, are called Hort, and at Russian turbomachinery school designated by Latin, small Latin letter B. But as far as I know, in foreign turbomachinery school, I used other letter. I don't remember which one. Sometimes S, sometimes C. It depends from the sources. But these parameters are very important because it have big influence to the gas dynamic efficiency, of course. It's have influence to the stresses, of course. It's influence to the manufacturing process and many other processes. That's why it's very useful parameters in all areas deal with the turbomachinery. The angle between the Hort and the front in Russian turbomachinery school are designated by Greek letter gamma. This is a stager angle, this one. This is gamma, this is B. Very often we are use term axial Hort. This is length of the blade row in axial direction, and we are usually use as a designation to designate the axial Hort. At this picture, it's this parameter. And if we are return back to the previous slide, we are already speak about this parameter, this one, SA. This is axial Hort, and this parameter connect these two pictures. Picture of parameters of meridional cross section and picture of parameters of blade row. So what else? What else? Let's change the color. So other main parameter. Okay, maybe I will return 1 second. So let's try to draw the chamber line for this blade and change the color. So let's make the tangent line to the chamber line at the point number 1. This is tangent line to the chamber line. Of course, for me it's very hard to draw straight line, but I hope you understand me. And we will do the same at the point number 2 for the trailing cage. We are draw tangent line to the chamber line at the outlet. So, by other words, we are create two tangent line which are tangent to the chamber line at the inlet at the outlet. The angle between this first tangent line and the front are called inlet construction angle, and for the rotor wheel designated by beta 1 blade index BL. So by other words, this angle beta 1 blade. And the same we could to do for the trailing cage. For the trailing cage, for the compressor, it will be this angle, beta 2. Section number 2 shows what we are speak about the section at the outlet of the rotor wheel. And index blade shows to us what we are speak about the construction angle. So, by other words, it's the metal angle. It's the angle of the construction. It's mean what you could to take the blades and you could to measure this angle using some tools. It's possible and it's really used during manufacturing process to control your detail after manufacturing. So, and here we need to speak about the angles. At this picture, you see what the typical rule of measurement angles which are used in Russian practice. So in Russian turbomachinery schools, especially in the turbine, typically we are measure angle from the front. We are start from this position and measure angles from the front at this direction for the compressor and at these directions for the turbine. So I pay your attention what it's the special feature of Russian turbomachinery school. I think it's only traditional, but at different turbomachinery schools, especially in England or at USA turbomachinery schools, I used other approach to measurement angles. And because you live in Europe, you could to use English textbooks with higher probability, and you need to pay your attention here because the moments which I will explain to you could be changed. I mean formulas could be changed in if you will use English and American turbomachinery books. Because usually in English and American turbomachinery schools, angles are measured from axial direction, like this. And of course, it's changed the formulas which you use during calculation process. That's why you need to take it in account. I think especially for you, it's important. But it's really traditional of every turbomachinery school how to measure the angle. The green one are typically for Russian school, the red one typically for USA turbomachinery school, but it's not the two possible position. In reality, the methods of angles calculating could be other. And for example, I remember one master degree work from Lund University in Sweden. The guy who created this master degree investigate the different models of which are described the losses in the turbomachine in the turbine blade throw. And he used different models from different countries, including Russians, including German, including English models. And he set 2 or 3 pages with the different cases how the different model are measure the angle. So it's only traditional, but you need to keep it at your head, at your head, what you are could to find the other approach to measure the angle, because it's really have influence to the formulas. So let's return back to the definition. The beta 1 and beta 2 blade angles, this is construction angle. But the flow to the leading edge, this the velocity W1, and this the angle beta 1. So if we comes to this picture, more accurate picture, this red vector will be inlet velocity W1. In reality, this is really a relative velocity. And the angle between the front and flow vector will be beta 1. So I pay your attention what we have two beta 1 blade or beta 1 angles. Beta 1, this one, and beta 1 blade. Two very close designation. If we will use index blade, it's mean what we are speak about the construction. If we will not use it, simple beta 1, it's mean what we are speak about the direction of the vector. Very often these two angles approximately the same. We are usually very close, especially at design mode. It's typical design practice, and if you will make these two angles approximately equal, it leads to low losses. That's why it's the typical design practice. But of course, in reality, especially in off-design condition, these two angles are not equal, and we have some difference between these two angles, and in our practice it's designated by letter I, and it's called incidence angle, this one, or angle of attack. It could be calculated like beta 1 blade minus beta 1, and it's mean what this angle have the sign. It could be negative or could be positive. For example, at my picture, incidence angle are negative. If we look to this picture, here incidence angle are positive. The value of incidence angle or angle of attack depend from the flow condition, depend from operating mode, and it could be changed during operating process, and especially for the compressors, it could be reason of unstable processes, it could be reason of the separation of the flow. At the outlet, we have approximately the same situation. The flow leave the trailing edge, this the velocity W2, this the angle beta 2. The direction of the vector W2 are determined by the shape of the blade at outlet part, but of course, in reality, the angles beta 2 blades and beta 2 are not the equal, but in usually they are very close. The difference not so big, not more than I think 2 degrees, but of course they are not equal, because we have the pressure difference between the pressure side and the suction side, and this pressure difference try to turn the flow after the trailing edge. And the difference between these two angles are designated by Greek letter delta and called deviation angle. So if we will use this picture, this will be beta 2 blade and this better too simple. So a little bit different picture because this picture for the turbine. So what else? What else? Okay, let's look what I forgot to set. The distance. Let's change the color. The distance between the same points of two adjacent profiles. So we are take the same points of two similar blades. These distance are called pitch. And in Russian practice used small Latin letter T to designate it. This one. Simply says it's the distance between the blades, but of course in reality it's not that true. It's the distance between the same blade of the nearest same points of the nearest blades. Of course these parameters are very important, and it influence to the working process, but of course it's influence to the because it determines the number of blades and other parameters, and it must be measured during manufacturing. And I pay attention what the pitch depend from the radius, and it will be different at different radius. 1 second. And for example, for the radial turbomachinery, sometimes you could use the pitch which are measured at angles. So typically we use meters or millimeters to measure the pitch. But sometimes you could use the angular pitch, which are measured in degrees for the radial turbomachinery. So other parameter, okay, other parameter. We have a lot of circles which we draw inside the profile. Of course, we have the biggest one of the circle, which will be the biggest. The diameter of the biggest circle which are drawn inside the profile designated by letter CM and called maximum thickness of the blade. Of course, these parameters are not determinate only gas dynamic parameters, or not only gas dynamic processes. It's have, for example, strong influence to the stresses, and that's why it's important. And usually we use next parameters which called the distance between the leading edge and the center of the maximum thickness. These parameters are designated like XC. It must be C. For example, during profiling process, this value usually sets in percents. We are going to create the profiles using ANSYS software. For example, for the compressors, you will set this value and set the maximum thickness at percents relative to the blade chord. So what else? Let's look to our picture. So throat. In Russian practice, we are using AG to designate throat. Simply says throat, it's the minimum what is it? Nearest place locate near trailing cage. So it's one of the main differences between the compressor and the turbine. What the throat position are different in the turbine near trailing cage, in the compressor near the leading cage. So, and of course, we could use some dimensionless parameters like solidity, like relative pitch, like blade aspect ratio, but I think we will not pay a lot of attention to it. So I will make short look. I think I'm not missed all parameters what I want to discuss with you, what I want to explain to you. So guys, do you have any questions?
No.
Perfect. Okay, let's continue. So let's speak a little bit about the classification of the turbomachinery classification. So we could use the very different approach to classify the turbomachinery. Some of them are present at this and at the next slide, and you will see what it's rather simple classification. So usually we have only two positions. For example, by the direction of energy movement, turbomachinery could be classified like machines engines. It's the machines which extract energy from the flow. By other words, it's the turbines. And machines performers, which supply the energy to the flow. By other words, it's the compressors, fans, and pumps. We already discussed it at one of the first lectures, but I think you understand what these classifications are not widely used. By number of stages, the turbomachinery could be one stage or multi-stage, and could be one cascade. It means what you have one rotating shaft, or multi-cascade. It means what you have two or three rotating shafts. You could have low pressure cascade, intermediate pressure cascade, and high pressure cascade. And you could classify the turbomachinery by the shaft position. Your turbomachinery could have horizontal X. It's typically, for example, for aircraft and industrial application, or could be vertical position of the shaft. It's more suitable for water turbines, like at this picture. This is Kaplan water turbine, but I know some examples then the industrial power turbine are located vertically, but it's not very usual. And other type of the classification by the number of inlets, single inlet or two inlet. Typically, if we speak about the centrifugal compressor, especially like at this picture, this type are more widely used, but sometimes, especially at the old engine, you could find two inlets. For example, if you find the construction of Russian VK1 engine, or its license copy of Rolls-Royce NIN engine, you could find at this engine two inlets centrifugal compressor. So I hope somewhere you will come to the Samara and we have the first one in our engine museum, and you could look how such type of the compressors looks in real life. So by the presence of casing, it could be open, could be closed. I think it's clear from the picture. And by pressure change, active and reactive, I think at this moment it's very hard to explain the difference. but we will try to use such classification when we will speak about the degree of reaction and degree of reactivity. So you see what we could to classify the turbomachinery by using different approach, but I think especially if you are already read some books with the explanation, this the how to say about the engines, these the technical parameters of the engines, you are not find all the classification. I think you are here only classification deal with the number of stages. So by other words, most useful type of the classification from from the types which are present at this slide, this one. You really could to find the how to say oh, sorry, I forgot the English word. So you really could to read the information what engine use three-stage axial compressor. So that's why it's mean you are using such type of the classification. But we have other type of the classification, and this type of classification are more useful in real practice. So the turbomachinery could be classified by the direction of the flow movement. And these classifications are common for any type of the turbomachinery. So, by the direction of the working fluid movement, the turbomachinery could be divided at the same group. First, axial turbomachinery, then the direction of the flow approximately correspond to the direction of the rotational x. So, it's not mean what the direction and x must be parallel. The direction of the flow could be a little bit deviate, maybe 10-15 degrees from the direction of the x. Such type of the turbomachinery are called axial turbomachinery, and here you see the example of axial three-stage low pressure compressor. This is low pressure compressor. So the next type, centrifugal compressor. The main idea, main special feature of such type compressor deal with the changing of direction of the flow. The flow comes in at the lower radius and turn into the rotor wheel to the radial direction and comes out in usually in radial direction in upper radius. So if we are write the radiuses, R2 will be more than R1. So the flow moves from the lower radius to the upper radius. Such type of the turbomachinery are called centrifugal turbomachinery. And the opposite picture, then the flows come in and in the upper radius, at the radius R2, R1, and comes out in usually in axial direction in the lower radius R2. At this case, R2 lower than R1. So, by other words, at this type of the turbomachinery, the flow moves to the direction, to the center. These two types of the turbomachinery sometimes are called radial turbomachinery. And of course, we have something mixed between it, which are called the diagonal turbomachinery. So, most useful, so what I want to say, the this classification are common for the turbine and for the compressor. The example, the images which are provided at this slide are for compressor, but we are not. This is turbine. There is a centripetal turbine. This picture is centripetal turbine. Only one exception. The centripetal compressors do not exist. In future, using some equation, I will try to explain to you what such type of the compressors do not provide high pressure ratio. That's why they are not used. I never see the centripetal compressor. Only at the picture, only at the scheme. So what else? What else? What else? The next moment. The axial and centrifugal and centripetal turbomachinery are widely used in real practice. I don't know, but the diagonal turbines and diagonal compressors are not widely used, but we have very promising characteristics between the axial and centrifugal stages. And maybe in the future we will use the diagonal turbomachinery, but now at real practice I know only few engines, few turbomachines which are used diagonal stages, but they really have the promising characteristics. Maybe the designers' method of such type of the turbomachinery are not developed yet, but I don't know why it's not widely used. So, I think that's all at this slide, and let's try to compare the characteristics of the different type of the turbomachinery. We will provide the comparing for the compressor stage. So, and here I will speak only about one stage. Of course, for example, if you look to this picture, you will see pressure ratio, and you could say, oh, we know what at the modern engine, the pressure ratio must be 14, 50. It's true, but we are speaking about the parameters only of one stage. We are not discuss here the multi-stage turbomachinery. So, if we will compare axial and centrifugal compressor, let's discuss the main parameters of axial and centrifugal compressor. If we speak about the axial compressor stage, the typical pressure ratio not more than 2 per 1 stage. So maybe a little bit higher. So for example, I know the example of stage of axial compressor is the pressure ratio 2.2 as far as I remember. But it's very close to the 2. So, but this number, I mean 2, it's the parameters of the future compressor stage. I'm not know the real application of such stages in real engines. Maybe it's present at some modern engines, but I don't know. In reality, the typical pressure ratio at one axial stage a little bit lower. For example, if you will make the the calculation of thermodynamic cycle, usually the guys who provide the thermodynamic calculation, if we need to find out the pressure ratio of the compressor. For example, you are calculating some prototype and you need to determine what the pressure ratio have, for example, high pressure compressor or intermediate pressure compressor. How to determine it? Because usually such information are not provided at the publications. So you could find out approximately value of pressure ratio of the cascades, and guys who provide the thermodynamic calculation usually used the value 1.35 as average pressure ratio of one stage of the gas turbine engine. So you could use this value to calculate, for example, pressure ratio of high pressure compressor. Other example, the pressure ratio of one stage of the fan of the turbofan engine approximately 1.7. So you see what it's lower than 2. If we will speak about the efficiency, the typical level of efficiency of axial stage approximately 0.9. The turbine have high efficiency, the compressor have low efficiency. For example, for the turbine, it's very typical efficiency 0.92, 0.93. Examples with the efficiency 0.9, 0.93 for the compressor stage. But of course, in reality, the level of efficiency of the compressor a little bit lower. But I think for you, it's better to remember what the level of efficiency of axial stage, middle level, approximately 0.9, 90%. So, let's discuss the centrifugal stage. The pressure ratio of one centrifugal stage, so below you could see the example of the centrifugal compressor, this one and this one, and of course I think you understand what it's the axial stages. So the typical pressure ratio of centrifugal compressor stage approximately 10. And this value, I find such values in some technical publication, and this is value of the future compressors. So that's why somewhere in the future, maybe we will find the centrifugal compressor stage with the pressure ratio 10-12. But today, in real practice, if we will speak about the turbocharging system, the pressure ratio per one stage approximately 3. For the gas turbine engine, it could be reach 5-6. But in any case, you will see what the pressure ratio of one centrifugal stage more than pressure ratio than one axial stage. So, and if we will speak about the efficiency of the centrifugal stage, the efficiency of the centrifugal stage will be lower. Here I provide the information from one textbooks, which have information what the biggest efficiency of centrifugal stage, 85%. But it's the efficiency of the future stages for the gas turbine engine. In reality, the level of efficiency a little bit lower, and the reason of such low efficiency, the complex flow structure. I think the typical level, typical useful level of efficiency of the centrifugal compressor stage, approximately 75–80%. So, and what's the conclusion? If we will compare axial stage and the centrifugal stage, you will see what the axial stage provide small pressure ratio but high efficiency, and centrifugal stage provide high pressure ratio but small efficiency. The centripetal and diagonal stages approximately something middle between the axial and centrifugal stages. And let's compare other characteristics of the turbomachinery stages. So, in any case, in any type of the turbomachinery, if you are reducing the mass flow rate through the turbomachinery, for example, you are designing the stage for the small gas turbine engine, and you not need big power and that's why you are reducing mass flow rate. In any case, when you are reducing mass flow rate during design process, the sizes of the blades will be decreased, and decreasing of sizes of the blades will be leads to the increase in losses. It will be factor which are reduce the efficiency. And that's why if you are reducing efficiency, all types of the turbomachinery, if you will reduce mass flow rate, all type of the turbomachinery will reduce efficiency. But the gradient of the changing of efficiency will be different. And for axial stages, the drop of efficiency will be higher. And at the mass flow rate approximately lower than 5 kg per second, the centrifugal compressor will be have higher efficiency relative axial stage. So what it means? What at the low level of mass flow rates, axial compressor will be have poor efficiency relative centrifugal stage. At the region of the high mass flow rate, axial turbomachinery will have advantage. So it's the first idea. And the second idea, how to create multi-stage turbomachinery. If we simply about the axial turbomachinery, you will see what it's very easy to create multi-stage compressor. You are simply set the second, third, and other stages after the previous stages, and you see this is stage number 1, this is stage number 2, this is stage number 3, and you see what you have no any additional channels, you have no steps in the flow path, you have no change in diameters. So the flow from the first stage simply comes into the second stage. That's why you have no additional losses and it's perfect. If we will speak about the centrifugal compressor, for example, this is the first stage, this is the second stage. The flow comes into the centrifugal compressor stage at the lower radius and comes out in radial direction. At the second stage, it must be comes in the lower radius and comes out to the upper radius. That's why you need to turn the flow 3 times by 90 degrees and supply your air from this region to this region. These processes increase the complexity of the construction and it leads to additional losses. And we remember what centrifugal stages have poor efficiency, and we receive additional losses because we need to provide additional turns of the flow. So that's why it's possible to create multi-stage centrifugal compressor and centripetal turbine, of course, too, but it will be leads to additional losses, and your stages will have poor. Your compressor will have poor efficiency. That's why such type of the compressors are not widely used, but sometimes you could to find it. For example, the first picture, this is Rolls-Royce, as far as I remember, Tame engine. It's the turboprop engine. It's rather old engine, and you could see what this engine have 2 centrifugal compressor stages. For example, in our engine museum, you could to find engine GTE 1000 for the tank, and then you will come to the Samara, you will find this engine, and you could to look how the multi-stage centrifugal compressors are look. Because the construction. Sorry. And here the example of industrial multi-stage compressor. You see a lot of stages of centrifugal compressor. Because this construction have high weight, high mass, and high complexity, it's not widely used in aircraft application, but here you see the real example from real practice. And as far as I know, the French company Turbomachinery widely use multi-stage centrifugal compressor on its engines for helicopters. You could find some examples of Turbomachinery engines. These are the multi-stage centrifugal compressors, and as far as I know, they are great specialists in the working process of the centrifugal compressor. So, this is brief to the parameters of the different type of the stage of the turbomachinery. And of course, at this moment, I need to ask you, what type of the turbomachinery stage will be better? What type of the turbomachinery stage we need to use in some machines? The right questions here will be the next. The application of the type, the choosing of the type of the turbomachinery will depend from the requirements which we have when we are designing our machine. So that's why let's study few examples. The first one. Let's try to find out which type of the turbomachinery are better for the gas turbine engine, for example, for aircraft. Before we will choose the type of the turbomachinery, let's find the requirements which are typical for the gas turbine engine, for example, for the civil aircraft. What is the typical for the gas turbine? What the requirements are typical for the gas turbine engine for the civil aircraft? Usually, it's the huge mass flow rate. For example, the engine like CFM56 have the mass flow rate approximately 315-400 kilogram per second. That's why typical mass flow rate for the gas turbine engine more than 10 kilogram per second. I hope you are already studied the cycle of the gas turbine engine and you know what the main tendency of the development of the gas turbine engine, increasing pressure ratio. And typically for the modern gas turbine engines, the pressure ratio at the compressors more than 30, 40 and leads to the 50 now at this moment. That's why pressure ratio at all compressor at the cycle rather high. And of course other requirements are the typical. Number of stages, number of elements must be minimum, efficiency must be maximum, complexity of the construction must be minimum. Finally, these three parameters will be leads to decreasing the cost of the aircraft. Cost of aircraft engine. So, and let's try to compare how which type of the turbomachinery will be more acceptable for the gas turbine aircraft engine. So, for this range of the mass flow rate, axial turbomachinery stage have the high efficiency. That's why here this type are more suitable. If we compare pressure ratio at one stage, we will see what we couldn't provide the compression which we need at one stage in any type of the turbomachinery. That's why we need to use multi-stage compression, and we remember what it's much easy, much not so complex to create multi-stage compressor from axial turbomachinery stage. So, and we see what the gas turbine engine for the aircraft most suitable will be use axial turbomachinery stage, because it's the better choice in the condition at which the typical gas turbine engine operate. So, and below at the bottom part of the slide you will see the example of real gas turbine engine. So this is Rolls-Royce Trent 900 engine, and you will see what we have axial compressors and axial turbine at this engine, and it's really typical gas turbine engine. But sometimes, for example, if you have design engine for the small aircraft and you not need to have high thrust, high power, the mass flow rate through the engine will be reduced, and finally the blade height at the outlet from high pressure compressor will be low, and that's why at such case at the last part of the high pressure compressor are used final centrifugal stage. And finally we receive axial centrifugal compressor. For example, this is engine from Pratt & Whitney company. Such type of the compressor are usual for the engines with the small mass flow rate, for the engines for this the small thrust. So, but typically for the gas turbine engines we are using axial compressor and axial turbine. The other example, let's try to find what the type of the turbomachinery will be better for the turbocharger system for the piston engine for the car. Of course, before we will start, we need to discuss the requirements which are typical for the turbomachinery, for the working process of the piston engine for the car. Typically, mass flow rate through the piston engines are rather small. I think it's lower than 1 kilogram per second. For example, I have the experience of designing compressors and the turbine for the turbocharging system for the train, and such turbocompressor have mass flow rate 3-5 kilogram per second. So by other word, the train, I think you imagine what the train have the powerful engine with the power more than typical car, have the mass flow rate 3-5 kilogram per second. Typically pressure ratio lower than 3, because if you will increase pressure ratio, it means what you need to decrease pressure ratio at the piston part, and it will be finally leads to the problem with the combustion of the fuel. And these requirements are the same like for the gas turbine engine, because you need to reduce complexity of your system and finally reduce the money which you spend for the creating, for the fuel consumption, for the construction. So let's compare different type of the turbomachinery. So at this region of the mass flow rate, radial compressor will be high efficiency. That's why we will say what here it's good. If we compare pressure ratio which could be realized at one stage, the pressure ratio of the pressure ratio of 3 could be realized at one stage of centrifugal compressor. But if we will use axial compressor, we need to use multi-stage compressor. So it means what we have choice using multi-stage axial compressor and one-stage centrifugal compressor. Of course, the construction of one stage will be more simple, more cheaper. That's why we need to use this one. And finally, we could to make the conclusion what for the condition which are typical for the cars, for the turbocharger system, is most suitable radial turbomachinery. And typical turbocharging system looks like at this picture, and you see centrifugal compressor and centripetal turbine. So here flows comes in axial direction and comes out at radial direction. At the turbine, the opposite picture. The flows come in radial direction, comes out at axial direction. So here, the turbocharging system, but you will see what this turbocharger system used centrifugal compressor, but axial turbine. These turbocharging system are produced in ABB company. And why this system I use axial turbine? It's mean what the mass flow rate through this turbine rather high. And if your mass flow rate will be 3-5 more kilogram per second, for you will be more suitable to use axial turbine, because this type of the turbine will be provide the better efficiency than centripetal turbine. That's why if you see the turbocharging system, this axial turbine, it's mean what this turbocharging system are used in the powerful machine. I think it will be a train or ship diesel engine. So that's why final conclusion here. For the condition of the piston engine for turbocharging system, more suitable to use radial turbomachinery, and typical turbocharging unit consists centrifugal compressor and centripetal turbine. But sometimes in the case of the high mass flow rate, you could use axial turbine because it's provide better efficiency. So that's all about the classification. Do you have any questions, guys?
No.
No. Okay. So we have half hour. Okay, guys. At the next part of this chapter, I am going to discuss the different area of application of the turbomachinery. I want to show to you what turbomachinery have very wide area of application, and I want to show to you what you could to use the knowledge which I going to do to you, to give to you in very different areas. Sometimes it's very unexpected areas, and that's why at the next lecture and at the last part of this lecture, we will discuss the application of the turbomachinery. So, and of course, for us, like for the specialist in the gas turbine engines, the main area of application of the turbomachinery will be deal with the gas turbine engine. So, and very soon, maybe today or tomorrow, I will prepare for you task, deal with the application of the turbomachinery. In few words, it will be small search. I will give to you the plane. You will need to analyze the plane characteristics and find the competitors of this plane and try to find what type of the engine are used at this plane. And after that, you will take this engine and you will study the parameters of this engine, and you will find the main competitors of this engine, and finally you will find the turbomachinery which are used at this engine. So maybe it's not very clear. I will write the email for you, but I want what you are make the search which are starting from the plane and ending to the turbomachinery. So we are starting from the plane, we are trying to understand the conditions, the requirements, the special features which deal with the engines of some type of the aircraft. After that, we are trying to find the information about the engine and try to find the main competitors. And after that, you are find the turbomachinery which are used in the at exact your engine, at exact your plane. So I think it will be better to write letter to me, but at few words you will achieve such tasks. So you need to present this work, the results of this work, like the presentation, and maybe it will be good idea to draw, to create video with your presentation. So I will send to you the examples. Unfortunately, it will be on Russian because these examples are provided by Russian students. But I think you will understand what I want from you. Okay?
Okay.
Let's discuss the working process of the gas turbine engine. So you are I hope you are the specialist in the gas turbine engine. And I don't know how about you, but if we will speak about the Russian students, it's very typical what after the finishing, after the graduating of our institute, we don't know how the gas turbine engine operate. I don't know why, but it's really the problem. That's why I think it will be good idea to refrain of gas turbine engine because you will hear my position, you will hear position of other professors, and finally you will construct your own mention about the working process of the gas turbine engine, and I think it will be for you. It will help to you to better understand it. So, if we will speak about the principle of operating of gas turbine engine, I know 4 explanations how it works. It's really strange, but I know 4 explanations. So, let's start from the most simplest explanation. The most simple and most short explanation sounds the next. The gas turbine engine, this is the heat machine which works using closed thermodynamic loop, closed thermodynamic cycle, and as results of realizing of this thermodynamic cycle, it's create the work, it's create the power, and this power are transferred to the energy of the moving of aircraft. It's very short. It's correct. If you will try to understand, every word are correct. But in my opinion, it's not clear. It's not clear why the engine provides the thrust. That's why it's only like example of the first explanation. The second explanation, very typical explanation, and usually then you will read the principle of gas turbine engine operating process at some textbooks or you will look some movie, you will find the second type of explanation. Second type of explanation usually describe how the working fluid comes through the engine. Typically, it sounds like the air comes into intake. It's a little bit compressed and direct into the compressor. In the compressor, the pressure are increased, and after that, compressed air supplied to the combustor chamber. In the combustor chamber, we are supplying heat because we have burning inside the combustor chamber. After that, exhaust gases expand in the turbine, and because we have expansion, we receive mechanical work in the turbine. And this mechanical work we are supplying to the compressor, and this energy used to drive the compressor. And after the turbine, exhaust gases expand at the nozzle, and finally we are receive high-speed jet with the velocity cs. It's from Russian nozzle, cn we could to draw. And based to this equation, we are receive the thrust. I think you know this equation. Maybe you use other letters, but you know this equation. In Russian practice, it's called Stechkin equation. But in reality, this is equation of conversation of momentum, of fluid momentum. So I hope you know this equation. Maybe you use other designation, but this is thrust. This is mass flow rate through the engine. This one, velocity at the nozzle. And this is flight velocity. And this is mass changing coefficient because you extract some air at the engine, you are supplying fuel. That's why you need to take in account changing of the mass, then the working fluid come through the engine. So this is mass conversation, not mass, momentum conversation equation. In Russian practice, it's the Stechkin equation. So I think it's the time to listen the better English than mine, and I'm going to show to you movie, some animation from France, I think, but on English, which illustrate this explanation. Okay, let's try. Let's try. 1 second. 1 second. This one. Do you see the video? Guys, do you see the video?
No, no.
No? Okay, let's try. This one. And now?
Yes.
Okay, I want to. So you see it. This is very high quality explanation, very typical explanation of the working process of the gas turbine engine. That's all. So it's very typical explanation, very good explanation how the gas turbine engine operate. But I think you see what it's rather boring explanation. But of course, it's very high quality explanation. That's why. That's why the explanation number 3. Do you see my screen? Okay.
Yes.
Explanation number 3, my version. So let's start from the Stechkin equation. If we look carefully to this equation, you will see what for the creating thrust we need to high-speed jet. So we need jet which flow with the high speed, and the speed of the jet must be more than flight velocity. What element could be provide the high-speed jet? So let's imagine you could to find any element you could to bring it at your room, and it's help to you to receive high-speed jet. So what element provide high-speed jet? Guys, do you have any version? What unit, what element could be help to us to create high-speed jet?
The combustion chamber.
Combustion chamber, good trying, but I'm not agree with you. So, for example, at your kitchen you have the combustor, but it's not provide high-speed jet. It's only combust. What else? No.
The compressor.
Compressor. No, guys. So you need to use nozzle. You need to use conical nozzle, Laval nozzle. It's not depend. So to create high-speed jet, you need to find to use nozzle. But if you will find the nozzle, it will not provide high-speed jet. You need to make some additional requirements. You need to provide this is nozzle. You need to provide the pressure difference between the inlet and the outlet of the nozzle. So, to create high-speed jet, you need to find nozzle, but nozzle without anything will not be work. You need to provide additional conditions. You need to provide the pressure difference between the inlet and the outlet. And the pressure at the inlet of the nozzle will be more than pressure at the outlet of the nozzle. At this case, you will achieve high-speed jet at the outlet. How we could to provide pressure difference? We have two ways. First, you could create vacuum at the outlet, but it's very hard, but sometimes it's used for the tests. But in real practice, we are more often create high pressure at the inlet of the nozzle. And the next question for you. What unit, what device provide high pressure? So what device provide high pressure? Guys?
The compressor.
Yes, perfect. So we need to set up the compressor before the nozzle to create high pressure before the nozzle. So, and we are set the compressor. And let's imagine we are create the engine which are consist from the compressor and the nozzle. And we are imagine what the compressor will compress the air and supply it to the inlet of the nozzle. And finally, we are receive high-speed jet. But this engine, which consists only from these two elements, will be not operate. Why? Very simple. We need to supply mechanical work to the compressor to rotate it. That's why we need the source of energy which will drive the compressor. So, and we need source of energy. But in reality, here you could to use any source of energy. You could to use electrical motor, you could to use piston engine, you could to use turbines, you could to use slaves, you could to use any device, steam machine, for example, any device which create mechanical work. But usually we are used turbine because turbine allows to us receive huge power but have very small sizes. And now we are receive the next construction. We are receive the engine which are consist from the compressor and from the turbine and from the nozzle. And very interesting but not very simple question. Will be such engine create the thrust? Guys, do you have
No.
any? No. Why?
Because we need additional power.
Additional power for what?
Because the power is used by the turbine to run the compressor, so we need power to add speed.
I think you in common you are true, but I think it's not clear for for everybody. Yes. So to understand why this engine will not operate, let's draw PV diagram of the cycle of this engine, exact of this engine. This is specific volume, this is pressure, and let's start from the point number 1. We are take the air, this such condition, and became to compress it. And we are provide adiabatic compression in the compressor. And adiabatic line will be looks like here. The specific work which you need to supply to provide compression equal to this area. This area equal to the specific work which you are supplied during this process. But you will see what in our case, when we have no combustor, point number 2 and point number 3 will be the same. It means what the expansion process will be start from the same point like the end of the compression process. It's the first moment. The second moment, the expansion process will be adiabatic too, because the turbine expansion in ideal case adiabatic too. And the last idea, the specific work of the compressor, at such case, if we will not take into account losses, if the mass flow rate through the compressor and through the turbine will be the same, specific work will be the same for the compressor and for the turbine. And we know what the process in the turbine is adiabatic, and it's mean what it will be comes through the line to 1, and specific work of the turbine equal to the specific work of the compressor, it's mean what the final point number 4 will be the same with the point number 1. But pressure in the point number 1, it's equal to point at the outlet of the engine. And it's mean what these 3 pressures are equal, and it's mean what we have no pressure difference between the nozzle. Oh, sorry, between the inlet and the outlet of the nozzle. And it's mean what we have no, we are not receive high-speed jet. That's why such type of engine will not create the thrust. Maybe the rotor will be rotate, but the thrust will be not created. How to solve this problem? To understand it, let's draw the equation for the adiabatic expansion. This is adiabatic specific work, and it's determined by specific work of the compressor. This is CP, is a baric heat capacity. Inlet temperature, it will be T3 in our designation. 1 minus P4, P3, it's the total pressures in degree K minus 1 minus K. K, it's in Russian practice adiabatic index. Maybe you use letter gamma to designate it. I don't know how in the France, but sometimes foreign students use gamma to designate it, but this is adiabatic index. So this value determined by the specific work of the compressor, and we are fix it. And if we look carefully to this equation, if you will increase total temperature before the turbine, you could to increase pressure P4. So, by other words, if you will increase the temperature before the turbine, you will receive the same specific work with the lower pressure ratio. That's why, if you will heat the gases after the compressor, you could to receive the pressure ratio, you could to receive the lower pressure ratio in the turbine, and it's mean what you finally receive high pressure at the outlet of the turbine, and will find the condition for the creating of high-speed jet. So that's why you could to use any device which will increase the temperature. In reality, it could be any device which you want. It could be combustion chamber, it could be heat exchanger. Sometimes the heat exchanger are used in gas turbine engine, for example, for the engine with nuclear reactor. Some countries, a lot of time ago, some countries, USA and Russia, I mean, try to create gas turbine engine with the nuclear reactor, but they are not use it in real life because it's very dangerous, of course. So that's why this explanation, in my opinion, shows the role of each element of the gas turbine engine. I like this explanation because it's clear, shows to you what you need to do, what the position of each element. For example, if I ask to you, please explain to me what will be happen if we remove the turbine. You are very simple could to explain to me what if we remove the turbine, the compressor will not be operate, and it's mean what we have no high pressure in the inlet of the nozzle. It's this idea. And the next moment you could ask to me, okay, the aircraft engine creates the thrust, but what will be if our engine are not for aircraft? What will be if our engine for the drive of electrical generator of gas pumping unit? And such type of the engine create the torque, create the rotating output shaft, the main result of working process of power ground unit, rotating shaft, which are connected to this electrical generator. And this rotating shaft rotated by turbine. That's why for the creating of output power for the power ground unit, you need turbine. But what condition you need to create to start the turbine operating process? You need to create pressure difference between the inlet and the outlet. And finally, you have the same condition like at this moment. You need the K element, and you need to provide the pressure difference between the inlet and the outlet. You need to provide high pressure at the inlet of the K element, and after that you are built this moment. So we will skip it. Only pay your attention what the working process of the gas turbine engine in reality similar to the working process of the piston engine, but in the piston engine, engine works with the isolate volume of the working fluid. In the gas turbine engines, all processes take place at the same time and continuously, and that's why you are finally receive very high mass flow rate and very unique parameters. So, and this picture shows the parameters distribution. We will not spend so much time to discuss it. I'm only want to pay attention at one thing. So, as we are say above, the key element of the aircraft gas turbine engine nozzle, and to create thrust, we need to create the pressure difference between the inlet of the and outlet of the nozzle. By other words, we need to create high pressure at this section. So, and this part of the engine, compressor combustor turbine, it's very complex. It's very high cost element, and engineers spent a lot of money, time, and efforts to create this part of the engine. But result of working process of this part is only jet of the gas with high pressure and high temperature. For me, it's very scary idea. So we make so lot of efforts, so lot of money, so lot of time, only for creating device which create jet of the gas with high pressure and high temperature. it seems what maybe somewhere we have the way to create the same with the lower efforts. That's such scaring idea. So this is third explanation of the working process of the gas turbine engine. And the fourth explanation, one second. Fourth explanation, the funny explanation. So guys, I understand what our lecture is over, but let's look small movie, approximately 5 minutes. It will be fourth explanation of the working process of the gas turbine engine, but I think it's very interesting. So 1 second. I will share the movie. I lost it. So do you see it?
Yes.
Okay, let's look at the movie, and after that we are finishing the lecture. You see what happens. So, such interesting movie. So I think it's the most interesting explanation, the principle of operating. And I think for you it's interesting twice because you see what this movie was created in French company. So guys, I think you understand what the working process of the gas turbine engine strongly connect the working process of the compressor and working process of the turbine. And for example, using of the turbine allows to us to reduce sizes, reduce weight of the engine, and that's why we are using it. And that's why the turbomachinery is the main component of the gas turbine engine. I hope what this part of the lecture help to you to better understand the working process of the gas turbine engine and the position of the turbomachinery in the gas turbine engine. So, I think it's enough for today. Do you have any questions? So, and soon, maybe today, maybe tomorrow, I will send to you the task by email, of course. So, do you have any question?
No questions. Thank you.
Okay, perfect. Okay, guys, thank you for attention. I hope it will be helpful for you. It will be interesting, I hope. So see you at the next time, at next week, at Monday, at the same time, at the same link. If you have any questions, please write to me.
Okay.
Okay.
Okay, thank you.
Thank you.
Thank
for
you. Bye.
attention.
Thank you.
Bye.
Goodbye.
Bye.